Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. In the Unit 1, we will be studying about stereoisomerism Part 1. In the Lecture 2, we will be studying about elements of symmetry. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this particular session, we will be studying about symmetry elements. We will be studying about what is identity, proper rotation, reflection, inversion, and improper rotation. In this session, we will be studying about elements of symmetry. We are all fascinated by elements of symmetry. If you look at the beautiful Taj Mahal, it is having an exact mirror image. Exactly one half of the Taj Mahal is the mirror image of the other one. It is having a very beautiful symmetry. And there is another one which everybody likes is a butterfly. It is also having a C2 axis of symmetry. So it is having exactly the mirror image at the center. And if you look at a beautiful honeycomb structure, it is having a hexagonal structure. So these are all various elements which we look or which we enjoy in our everyday or day-to-day life. So symmetry is actually ingrained, and even if you look at the human being, so externally we have a C2 symmetry. So that we have right hand and the left hand, right eye, right leg, left leg. So if we can exactly break our body into two pieces at the center, we will have an exact mirror image. So in other words, human beings are very much fascinated by symmetry, and in organic chemistry we will study about some of the symmetry elements and what is the requirement for the compound to be optically active and how optical activity and symmetry are interrelated to each other we will be looking at now. So why we study symmetry? Simply because to understand and explain some of the basic things about chirality. So why a molecule is chiral? In other words, if it is optically active, what is the requirement for the compound to be optically active? So that can be explained based on symmetry elements. And in fact, the 2001 Nobel Prize on Chemistry was given to catalytic asymmetric synthesis, where people had used chirality to specifically create asymmetric compounds, and this also explains why some compounds are optically active and what is the relationship between symmetry and optical activity. Basically, if a molecule is highly symmetric, then it is going to be optically inactive. So there should be some amount of asymmetry or dissymmetry is required in the molecule to show optical activity. And in the spectroscopy also we can study how the symmetric stretching and bending are involved. And the relative reactivity of the groups are also can be explained based on the symmetry elements. And orbital interactions, basically the electrocyclic reactions or pericyclic reactions, can also be used to study about symmetry. So these various things can be explained using symmetry elements. So that's the reason organic chemist and pharmaceutical chemistry people also study about symmetry very carefully. Especially in the case of drug development and other thing, chirality is very crucial. So stereogenic centers, how they affect the metabolism of a substance, whether the R isomer is active or the S isomer is active, or one of the enantiomer is active, the other one is not active. So all these things requires basic understanding of symmetry elements. So basically symmetry elements, what are the various symmetry elements we can study is an action is performed on a geometrical object, then it undergoes some change. The change can be viewed whether we are getting exactly the same original object after the operation, that is after the some of the elements of symmetry is applied. It can be with respect to an axis, plane or center of inversion, line or point. So basically we have to perform some operations on an object, and after the operation we have to check whether is there any change after the operation or not. Based on that we say the molecule or the compound has that particular element of symmetry. So basically we have various symmetry elements which are present, which is a mirror plane, proper axis, improper axis and center of inversion are the various symmetry elements, and the symmetry operations are basically performed with respect to the symmetry elements. So if we say there is a reflection, that means if there is a mirror plane in that molecule, then we can say reflection is expected. So these are all the symmetry operations. When there is a proper axis, that means during rotation the molecule will show whether it is getting the identity or not. The same way improper and the center of inversion are given here. So basically what we do is we perform the symmetry operation on the molecule and we say certain symmetry elements are present or not present. In other words, we perform the reflection. If there is a reflection plane, then we say the molecule has a mirror plane. So the same way we rotate the molecule and we say if we get a indistinguishable object, then we say the molecule has a proper axis. So basically we perform these operations to identify whether which symmetry elements are present. So this is how we can study our symmetry operations, and symmetry elements are interrelated to each other. And we can say there is different levels or the dimensions of symmetry. So plane is basically a two-dimensional element. So when there is a mirror plane, we say it is having a 2D symmetry, and the line or axis is basically a one-dimensional one. So the proper axis and the improper axis are basically the one-dimensional symmetry elements that can be present in a molecule. And if it is a point one, that is center of inversion is present, that is a zero dimension, then we have all the three dimensions, 2D, 1D and zero dimensions, which are represented by the various symmetry elements. Let us look at the identity operation. So here there is no change in the structure after performing the identity operation. So every object has an identity and it is represented as E, that is Einhard, that means German unity. So if you perform identity operation on this molecule, we exactly get the same molecule. That means doing nothing is basically an identity operation. Then we have proper rotation. So this is basically the rotation about an axis by 360 by n. So if we take a linear water molecule, this is very similar to an example of water molecule. Here 180-degree rotation gives the same identical structure. So we say this is having a C2 symmetry. And if we take borane molecule, this is rotating 120-degree produces the identical image. So we say this is having a C3 axis, and the cyclobutane ring is having a C4 axis, and the benzene is having a C6 axis. So let us look at the demonstration of this proper rotation. Let us look at the CN axis. This is a water molecule as shown here. This is having a C2 symmetry. So what we are going to do is we are going to do 180-degree rotation, and let us see whether there is a change in the starting molecule representation or not. So this is water molecule. I am going to rotate 180 degrees. So slowly I am rotating it. So this is 90-degree rotation. I did to 180-degree rotation. So when I do the 180-degree rotation, I am exactly getting the same representation as shown in the beginning. So that means this is what is called the C2 axis of symmetry. So once again I repeat the same thing. So I am going to rotate it. So we end up with the same representation. So 360 degree divided by 2 times, because in the first time at 180 degree we have the first representation which is similar to the initial one, and after another 180 degree rotation, that means 180 plus 180, 360 degree rotation, we are again getting the same thing. So 2 times we are getting the same representation as the initial one. So 360 degree divided by 2 is 180. So in other words, this molecule is having a C2 rotation axis or C2 symmetry. So the molecule shown here is the boron molecule. Boron is in the center. 1, 2, 3. 3 hydrogens are shown here. So this boron molecule is having C3 axis of symmetry. So now we have to see what is the C3 axis. I have to rotate the molecule through 120 degree on the plane. So the first, it is at the top, one of the hydrogen is at the top, other hydrogen is on the right hand side, one more is on the left hand side. I am going to do a 120 degree rotation on the plane. So when I do the 120 degree rotation, I am getting another exact replica of the first or the initial image. I am going to rotate another 120 degree. So this time I am getting the second time the replica of the first one. I am doing another 120 degree, which leads to the third time. So that means in a 360 degree rotation, 3 times the same starting representation was seen, identical to the initial one. In other words, 360 divided by 3 is 120. That is, the 120 is the degree we have rotated 3 times. So this molecule is having a C3 axis of symmetry. So this is a boron molecule. So this is having a maximum CNist C3 axis, and we also have another C2 axis for this molecule. If I rotate the molecule like this, perpendicular to the plane, I am getting an identical representation as the initial one. So that means here I have a C2 axis when I rotate like this. So this is perpendicular to the plane of the molecule. I get C2 axis. If I rotate on the plane of the molecule, I get C3 axis. So we have one C3 and one C2 which is perpendicular to the plane. So these are all the two axes or the axis of rotation for the boron molecule. So this is a cyclobutane molecule. In this molecule we have 1, 2, 3, 4 carbons are there. So if I rotate 90 degree, I am just going to rotate on the plane. Okay. So when I rotate 90 degree, I am getting an identical representation similar to the first one. I do another 90 degree. So in 180 degree I am getting 2 times, another 90 degree, third one, and another 90 degree. So in the 360 degree rotation I am getting 4 times the same representation as the initial one. So in other words, 360 divided by 90 is 4. So this is having a C4 axis of symmetry. So this molecule is having a C4 axis of symmetry on the plane of the molecule. Like the boron one, we also have a C2 axis. Let me show what is the C2 axis we have in this particular molecule. I am rotating perpendicular to the plane this time. Okay. So when I rotate perpendicular to the plane, I rotate 180-degree, I get the initial exact similar representation. I do another 180-degree. So this time also I am getting the same representation as the initial one. So this is having a perpendicular C2 axis. And we can also do this across this bond, and across this bond also we can do. So that way also we have another couple of C2 axes which are perpendicular to the plane. So this molecule has various C2 axes which are perpendicular to the plane of the molecule, and it has one C4 axis on the plane of the molecule. So this is your very familiar benzene molecule. So this is having 6 carbons, 1, 2, 3, 4, 5, 6. So this molecule can undergo C6 rotation, that is 6 times it will show the same orientation. So let us rotate on the plane of the paper. So first I am going to do a 60-degree rotation. So this gives the first identical representation. Another 60-degree, second one, another 60-degree, third one, another 60-degree, fourth one, another 60-degree, fifth one, another 60-degree, sixth one. So in turn we can say 360 divided by 60 equal to 6 times. So the 6 times the same representation is coming up. So this molecule is having a C6 axis of symmetry. So that is how we can say benzene is having a C6 axis of symmetry. And this molecule also has a C2 axis which is perpendicular to this across the bonds, and 1, 2, 3, 4. 1, 4 carbon atoms also can be used for the rotation of the molecule. If I keep this in the same plane, I rotate the molecule like this. So 180-degree rotation produces the first identical image. So another 180-degree rotation will give the second identical image. So that means this is having a C2 axis perpendicular to the plane of the molecule. The same way we have between the bond also we can have the same rotation. So the C2 rotation can also be done on this way. So this molecule has various C2 axes, and it is also having a C6 axis. The maximum N is generally called as the principal axis. So benzene has a C6 as the principal axis for rotation. Next, let us look at reflection. So reflection is basically about a plane that is very similar to placing a mirror. So we have 3 different reflection planes. One is a vertical one which generally passes through the CN axis or the principal axis. The second one is a horizontal plane which is mostly perpendicular to the CN or the principal axis. And the third one is the dihedral one or the diagonal one which is passing between two C2 axes. So these are all the 3 mirror planes which are present in various molecules. So we will be looking at one by one now. And what is the easiest way to remember is if you look at mirror, the last 2 letters are written as OR. So when you write them in a combined way, you write like this, sigma. So basically sigma plane, that is the reflection, is based on the mirror. So that you can remember, and it is generally represented as sigma as I shown. We will see the same examples what we have seen earlier. The first one is the water molecule. So this is having a sigma V plane. The next one is a borane molecule we saw, which is having a sigma V and a sigma H planes. And the third one is the cyclobutane we saw. It is having sigma V, sigma D and the sigma H. All the 3 planes are there. And similarly, the benzene molecule, which is having a C6 axis as the principal axis, also has sigma V, sigma H and sigma D. All the 3 planes are present here. Let us look at the 3-dimensional representation of this one. Let us look at the water molecule. If I draw a line perpendicular to this one, like bisecting the molecule into 2 halves, then this part of the molecule is exactly the mirror image of the other part. So we have a mirror plane as shown here, which is perpendicular to the plane of the molecule. There is also another plane. If I rotate the molecule like this, and I can exactly cut the molecule into two pieces. So that means the plane of the paper can be cut into two pieces because this is a planar molecule. So I can exactly cut the plane into two pieces to get the exact mirror image of each other. So this is another plane. So we have two planes in this molecule. One is cutting the molecule into two places which is perpendicular to the plane of the molecule. Another one is cutting along the plane of the molecule. So we have both sigma V planes and sigma H plane in the case of water molecule. Let us look at the water molecule. I can cut the water molecules perpendicular to this one. So we get two pieces of exactly the same molecule. So this is one of the vertical plane which cuts the molecule into two pieces. So the water molecule has one vertical plane. This is the boron molecule. If I cut the molecule from this hydrogen to this boron directly, so I get two half of the molecule. The same way, if I cut across this hydrogen and this boron, I will have another two piece. And from hydrogen to this boron, if I cut this way, I will again get two identical pieces. So there are three sigma V planes on this molecule. And if I rotate this molecule like this, and if I can cut, I will cut two pieces like this one. So this is also another plane which is available. So we have two different planes available for the molecule which can represent different types of vertical and horizontal planes. So this is cyclobutane molecule. As we mentioned here, the carbon number 1 and 4, I can exactly cut the molecule into two pieces. The same way across this carbon and this carbon also I can cut into two pieces. So the molecule has vertical plane of symmetry, and I can also cut the molecule between the carbon-carbon bonds like this way or this way. We have various planes of symmetry in this molecule. The same way, if I rotate the molecule like this, and I can also cut across this way to give the identical mirror image. So this molecule has both diagonal, vertical and horizontal plane of symmetry. So we have vertical, horizontal and diagonal plane of symmetry for cyclobutane molecule. So this is benzene. So similar to cyclobutane, here also we have both vertical, horizontal and diagonal plane of symmetry. So I can cut the molecules from 1 and 4th carbon, hydrogen passing through this one. So hydrogen, carbon, carbon, hydrogen. If I cut the molecule like this, I will get two pieces. And I can also cut between these two carbons bond and this carbons bond. So I can cut the molecule like this way also. And the next way is so I cut across this plane in which I get exactly the mirror image of the molecule. So this benzene molecule also has vertical, horizontal and diagonal plane of symmetry. So this way we can actually dissect the molecule to know what are all the different symmetry elements present in that particular molecule. Let us continue with the reflection or the sigma plane. So as we mentioned, water has C2V point group. That means it has a C2 axis as the principal axis and it has a vertical plane. And boron is belonging to D3H point group. So it has a C3 axis as the principal axis and three C2 prime axis which are perpendicular to the principal axis. And it has improper rotation, that is S3. We will see this later. And there is one sigma H and three sigma V planes. So those horizontal and vertical planes we had seen for the borane molecule. And in the case of cyclobutane, it belongs to D4H point group. So it has a C4 axis, which we have already seen earlier. And when we come to the sigma V planes, it is having one sigma H and 2 sigma V and 2 sigma D. So sigma V is basically between 1 and the third carbon, as I mentioned in that earlier case also. 1, 2, 3. So between 1 and 3 carbon, if I cut the molecule, we get the sigma V plane. And when we cut between the bonds, between 1 and 4 carbon and 2 and 3 carbon, so this, when we cut across the bond, then we get a sigma D plane. And if since it is a planar molecule, we have the other horizontal plane present on that itself. And when we talk about the benzene, we have seen it has both the sigma H, sigma B and sigma D plane. So when we cut between the bonds, it gives the dihedral or the diagonal axis or the diagonal plane. And if we go from 1 to 4 carbon, if we cut the molecule into two pieces, that is the sigma V plane. And since it is a planar molecule, we have the sigma H plane. So with all the various C6 principal axis and the sigma V planes and improper axis of rotation, we can say benzene belong to D6H point group. The next one is the inversion. So in the inversion, we are talking about the point or a center of the whole molecule. So from this center, if I go in the opposite direction and if I meet the same atom or group in opposite direction for every place, then we say this molecule is having inversion. That means for any atom in the molecule, an identical atom should exist diametrically opposite from the center at an equidistance. So for Y, we have one at the top and one at the bottom. For X, we have one at the top and one at the bottom. And for the Z, we have one at the left hand side and one at the right hand side, all from the equidistance from the center. So this is what is called inversion center, or the point of center of symmetry for this particular molecule. The next one is improper rotation, and it is given as Sn. In this particular improper rotation, what we have to do is, there are two operations involved in this particular case. One is the proper rotation, that is 360 degree by n around the principal axis, that is the Sn axis, and followed by reflection across a plane perpendicular to the principal Sn axis. The example given here is the allene molecule. So in this allene molecule, first what we do is a 90-degree rotation, that is the principal axis is 4, n is equal to 4, and which on rotation produces this particular representation, which on reflected on a sigma V plane produces this one, which is identical to the starting one. So we say allene with this particular X and Y groups has a improper rotation, and here the n axis is 4, so this we say it is having a S4 axis. And let us compare the relationship between symmetry and the chirality. Basically, dissymmetry is something that is called as when a molecule does not have reflective symmetry element, that is Sn axis, Sn symmetry element should be absent in the molecule, then the molecule is said to be chiral. That means if a molecule does not have reflective symmetry elements, then all dissymmetric objects are called chiral compounds or chiral molecules. And when we talk about asymmetry, the asymmetry means the molecule does not have all symmetry elements. So there is a difference between dissymmetry and asymmetry. So dissymmetry mainly talks about the improper rotation only, whereas asymmetry talks about all the symmetry elements including the Sn axis. So that way we can differentiate whether the molecule is chiral or achiral. So when there is a dissymmetry or when there is asymmetry, the molecule is said to be chiral. And basically, when a chiral object, if you say, is not superimposable with its mirror image, in other words, these are enantiomers, then the molecule is said to be chiral. The existence of the reflective symmetry, that means Sn axis is sufficient to make sure that the molecule is achiral. So if there is one single SN axis in that molecule, then the molecule is said to be achiral. Similarly, chiral objects do not have any reflective symmetry elements, but they may have rotational symmetry axis in some cases. So these are all the relationship between symmetry and chirality. So all chiral compounds should not have any elements of symmetry. So that is where we say dissymmetry or asymmetry of a molecule. So this is mainly applicable to the molecule as a whole, because when we say stereogenic center, in some cases, especially we will be studying about the axial symmetry and helical symmetry and other symmetry operations, the molecule as a whole is achiral. But if you look at the individual carbons, they may or may not have any chirality at the individual atoms level. But if you take the DNA helical structure, that is having a helicity, right-handed helicity or left-handed helicity is present in DNA structures. So they are basically chiral. Similarly, the protein structures also, as a whole, the molecule is observed as a chiral one or achiral one, not at the individual atoms or the groups level. So that is also possible. In many cases, the individual atoms may not be chiral, but the molecule as a whole can be chiral due to planar symmetry or helical symmetry or axial symmetry. In summary, we have studied about various symmetry elements, basically what is an identity operation, what are proper rotation, what is the principal axis, what is reflection, what are the different planes of reflection, vertical plane, horizontal plane and diagonal or dihedral plane. We also studied about inversion and improper rotation and the relationship between symmetry elements and chirality. With this, we conclude this session. Thank you.